lesson for 7.1, slope fields and Euler's method. And Euler's method is not on the AB exam for AP Calculus, so that is something that we are actually going to be skipping. So you may see some of the things dealing with Euler's method if you watch the video that goes along with the textbook, but I will not be covering that in my lesson. So first we have here differential equation is an equation involving a derivative. The order of a differential equation is the order of the highest derivative involved in the equation. So this chapter 7, this is really where we're going to start looking at antiderivatives without finding area under curve. We're actually going to be doing anti-differentiation. So we're going to be thinking backwards, thinking about what the original equation could have been. So that leads us to our first example. Find all the functions that satisfy dy dx is equal to secant squared x plus 2x plus 5. For 7.2, you will see a, trying to think of the right word here, handout. There we go. A handout will load that has some of the anti-differentiation formulas on it. But for this section, you're just going to have to think about the derivative in reverse. So dy dx, that's going to be y equals, well, the original equation that would give you a derivative of secant squared is tangent. The original polynomial that would give you a derivative of 2x is x squared, and the original polynomial that would give you a derivative of 5 is 5x. Now, because the derivative of a constant is 0, we don't know if there was some number tacked onto the end of this original equation or if there was not. So you do need to put a plus c at the end of all differential equations if you have no way to find what that original c was. So we were talking about integrals back in chapter 6. These are called indefinite integrals because you don't necessarily know what the value of that c was. And you don't have any bounds. That's even the more important thing. You don't have any bounds for this. So we don't know, we're not really looking at area under a curve. It doesn't really apply here. Whereas in chapter 6, those were mostly definite integrals because you knew you were going from point A to point B on your graph and you were looking more at an area. So this would be the solution for example 1. Y equals tangent of x plus x squared plus 5x plus c, because when you take the derivative of this equation, you end up with the dy dx from the previous step. Now, occasionally, they will give you a point so that you can figure out what the original c value was. And in this case, we know our original point is 1, 0. So I'm going to use the same process that I did for the previous question, but instead of just leaving my c on the end, I'm actually going to plug in for my x and my y with 1 and 0 respectively, and I'm going to solve for the c. And I think we actually did this back in chapter 4 in a few places. So this is something we have looked at before. So dy dx is going to give me y equals, well, the term that would give you a derivative of e to the x is e to the x. And then minus 6x squared would have to be a minus 2x to the third. The formula there is actually you add 1 to the exponent whenever you have a polynomial, and then divide by the exponent. So I would add 1 to the 2 and get 3, and then I take the 3 and I'm going to divide the 6 by that 3. That's how I get the minus 2. And then, of course, we have our plus c on the end. So now I'm going to go through and plug in. I have 0 equals e to the first minus 2 times 1 cubed. So that's e, and then 1 cubed is 1 times negative 2 is negative 2. And then to solve for the c, I'm going to get 2 minus e. So my c value is 2 minus e, which means my equation for y is e to the x minus 2x cubed plus 2 minus e. So you see, just because you're finding a c value that's a constant. It doesn't mean that it couldn't have a pi in it, that it couldn't have an e in it like this one did. C doesn't always mean just a regular rational number. Okay, here's our next one. Find a particular solution to the equation below whose graph passes through. Again, I'm given a point that has an x and a y value. So I'm going to do my antiderivative here. I get y equals x squared minus tangent of x plus c. Make sure you do not forget that plus c. Now we're going to go through and plug in. So I have 3 equals 0 squared minus tangent of 0 plus c. Well, the tangent of 0 is 0. 0 squared is 0. So in this case, my c value is 3. So my full equation is y equals x squared minus tangent of x plus 3. Example 4. This one is set up a little bit different because it says find the solution to the differential equation for which f of 7 is equal to 3. So 7, 3 is going to be my ordered pair. Now, this is not something I can find the antiderivative of. E to the negative x squared, that is not a nice question, but you can use one of the integral rules to go through to actually find this. So because I know I have to take the integral of both sides here, the integral of f prime of x is just f of x. If I do the integral of e to the negative x squared, well, again, that's not something that I can find, but I can force it to happen. And actually, rather than using x here, because x is what I'm plugging in, I'm going to change this and make this a t. Now it says here f of 7 is equal to 3. So that means if I make this going from 7 to some variable x, and I put a 7 in there, 7 to 7, anytime your upper and your lower bounds of an integral match, that is going to be equal to 0. And that's one of those properties that we talked about back in chapter 6. But I need it to equal 3 and not 0. I can fix that by just putting a 3 on the end. So not only, because when I take the derivative of this, I get an f prime. Taking the derivative of the integral, this is one of the fundamental theorems of calculus. The derivative of this integral means I plug in the x for the t, so I would just get e to the negative x squared. And of course, the derivative of the 3 is 0. So I do get the f prime line from above, and then if I plug in the 7 for the x, the integral becomes 0, and then plus 3 would give you a value of 3, so f of 7 would in fact equal 3. So this is a way to get a workaround if you can't actually find the antiderivative of what you're looking for. So examples 1 through 4, that is the first half of what this section goes over. The second half is all going to be dealing with slope fields. Slope fields are going to give you a graphical representation of what your potential differential equation could have originally looked like based on the slopes at different points. There is a program that you should have on your calculator, if I had a chance to put it on there, where you can do your own slope fields. If you don't have that program on your calculator, I'm going to try to link to some things online that you will be able to use to find the slope fields just rather than calculating them by hand. Now, you may have to calculate them by hand on an AP exam, but if you did, you would only have to do, say, 6 data points or at the most 8 data points. You would not have to do a ton of them, which is why I do want to make sure that you guys have the ability to do those using some type of technology. Okay, so first, it says graph the family of functions that solves the differential equation. So we're going to look at this the traditional way first. So dy dx is equal to cosine of x. So let's say that, or let's look at what I would have originally to get a derivative that's cosine. Well, I would have had to have a sine originally, and then I would have to have a c value. So we're going to look at what the different c values could be and how that would change our graph here. So I'm going to label this. This is going to be my negative pi. There's my negative 2 pi, positive pi, positive 2 pi. So the first one I'm going to start off with is c is equal to 0. Well, if c is equal to 0, then let's do and then negative 1, negative 2, negative 3, negative 4. So c is equal to 0. So for sine, negative 2 pi is 0. This is negative 3 pi over 2. That one, 0 at 0. And you can see we make this here's sine wave. It's a 2 pi period. And I have a width from negative 2 pi to 2 pi. So that would be the case if c was equal to 0. That's what it would look like. Now, let's take a look at, let's say c is equal to 1. So that would take everything in that graph and shift it up by 1. So it could look like this. And again, I don't know, even though the differential is cosine, I don't know what the original constant was. So that's why I have all these different options here. Let's say c is negative 1. That takes everything and moves it down 1. Your c could also have been a fraction. I'm not going to actually graph if it was 1/2 or negative 1/2, but it could be. Let's do one more here. Let's say my c was 3. So I would take everything in the blue line and move it up 1, 2, 3. And you can see every single one of these looks like the sine curve. We all get these nice waves here. So this would represent the entire family of functions that could solve this differential equation. And that's basically what a slope field does without actually having to find the equation for the original function. So we're going to take the same question. Well, here's the definition of slope field first. Your slope field is going to allow you to produce that family without solving it, like I just said here. So you can see this is an example of a slope field. It's a series of little tangent lines. Typically, if you need to graph a particular solution, they will tell you where to put a point, and then you're going to sketch something that matches. So let's say I knew that this point here had to exist. So I could come up and follow something probably like this, and I'd be able to sketch in what the original graph was without actually having to know the equation from the original. So this is going to be a slope field that we're going to construct for this differential equation. To construct the slope field, you're going to plug in different ordered pairs, and you're going to sketch out what the slope would be. Now notice this differential equation is only cosine of x, which means the y does not matter. In many of these cases, you will actually have to know the y and the x value to go through each of these. Notice I have my dots set up the same way that I did for the previous question that I did. So for example, if I look when x is 0 and y is 0, that would be the cosine of 0, which is 1. So anytime I have a y value of 0, or I'm sorry, anytime I have an x value of 0, it doesn't matter what y is because y doesn't really matter here. Any of the x values of 0, 1 is going to be my slope. So that's going to be actually the y-axis. So I'm going to have slopes of 0 at all of my 0 points. Again, the y, going up by the y's doesn't really change anything because they're all going to have a slope of 1. So where else is cosine equal to 0? Well, cosine is equal to 0 at pi. I'm sorry, I'm not thinking about the right thing. I'm looking at where cosine is equal to 1, and of course I did not draw that correctly. So let's go back and try that again, because those are zeros. I'm getting ahead of myself here. Let's try that again. So we have slopes of 1. That looks a lot better. So I'm drawing in little slopes of 1 everywhere that x is equal to 0. So now, again, let's go to what I was thinking I was doing before. Let's think about where cosine is equal to 0. Well, at pi, it's not equal to that. This is pi over 2 is where your cosine is equal to 0. So pi over 2 is going to be here. And again, the y's do not matter for this because it's always going to be 0. It's also going to be 0 at negative pi over 2, 3 pi over 2, and negative 3 pi over 2. So these are all going to be zeros. 0 slopes, little horizontal lines. Now we need to think about if there's any other places cosine is equal to 1. And I believe there are 2 other places where your cosine is equal to a positive 1. Cosine of negative 2 pi and a positive 2 pi are also equal to 1. So I have 1s here and 1s here. And then the other ones that I didn't do yet, cosine of pi and the cosine of negative pi, those are both equal to negative 1. So those ones are going to be going down. And you can see what we've just done here is we've drawn in a representation of where all of those possible family of functions could exist without actually graphing the correct solution. So let's say I know I have to pass through this point down here. That'd be 0, negative 1, 2, 3. That means that I could trace and see using, because it tells me what the slope is, so that tells me how to make my line. I could draw in the appropriate graph there. And you can see the graph that I drew in was a sine graph. But I didn't actually have to find that it was a sine graph in order to draw it. And that's why slope fields are so incredibly useful. So with this one, I'm not going to go through and construct all of this. I am going to do a few different points so that you guys can see how things work together. You will never have to do this many points in a homework assignment or on the AP exam, but I do want you guys to see how to do these. Notice it says particular solution that passes through the point 2, 0. So 2, 0 is right there. So that would be your starting spot for where you're actually going to go through and sketch this. So all you're doing is your name and your ordered pairs, plugging them in, and graphing the slope that you get. So the point 0, 0 is right in the middle, and that has a slope of 0. If I look at the point 0, 1, that's going to be 1. So 0, 1 is going to be 1. 0, 2 is going to give me 2. Notice I'm plugging in the x and the y value. So that's going to be a little bit steeper. 0, 3 is going to be 3, so that's even steeper. And then the next one, 0, 4, is going to be steeper yet. So you can see how that's going up. You should see some type of pattern here. For example, if we were to graph any combination like -1, 1, or 1, -1, those are both going to give me zeros. Anytime your x's and y's are of opposite value, then you are going to end up with values of 0. So 1, -1 is down here. 2, -2, 3, -3, 4, -4. -1, 1, -2, 2, -3, 3, -4, 4. So those are all 1s. And then you can go through -1, 0, which is this dot right here. -1, 0 would be a slope of -1. -2, 0, -3, 0, -4, 0. It's going to be more and more steep in the negative direction. 1, 0 would be 1, and then this one is going to be 2, and then 3, and then 4. And this is not going to be an exact science. It will take a little bit of practice to get these drawn correctly. And your book does go over this one, so I'm not going to finish this by going through and doing the rest of the points on here. So you can look and see how they go through and sketch the rest of these. This is another question I'm going to skip because you can, although we could talk about this a little bit and match them up, this would be something where it would be useful to use your graphing calculator to kind of match these up. But you can go through and see a couple things about them. For example, graphs A and D along the 0, x line, they both have slopes of 0. Well, number 4, x, when x is 0, it's undefined. And so that would be straight up and down, because undefined would be a vertical line. So that means 4 has to go to C, because you can see here that has vertical lines there. Now, the 2 times, excuse me, when x is 0, then I get 0. Both 2 and 3 would give me those results. So I know 2 and 3 have to go to A and D. But to figure out which one is which, we're going to have to think about where we would be undefined. So with number 3, for example, when y is 0, I'm going to be going towards those vertical lines because a slope that's undefined has a vertical line. And that's happening in A, not in D. Because in A, when I get closer to the x-axis, which is when y is 0, you see that I have my lines going up and down. So that means number 3 has to go to A. With number 2, looks like I'm going flatter as I go towards the y and when I go towards the x. So that means when x or y is close to 0, I'm going to be getting close to 0. So that one has to go with D. And then number 1, that leaves me with letter B. You can see, for example, if both x and y are 0, I do get flat. But as y gets bigger than x, I get negative lines. As y is less than x, I get positive lines. So those would all match up like that. This is your homework assignment. Should be for this section anyway. I am going to try to link some other videos so that you guys can get some additional guidance on slope fields. Again, it's not a huge part of our lesson, but it is something you guys will have to be able to work with and manipulate. So go back through, watch this video. I know it's a little bit long, but if you have any questions at all, you can reach out to me for help, or you can check on Khan Academy or check YouTube for any videos to guide you in your understanding.